Vector component. Vector component is useful because it's a notation that we can use to represent mathematically a vector, which will be very useful in cases where we have to add vectors together. So let's pick a vector A. And we will place this particular vector A in a given coordinate system x and y. We will consider a case of a two-dimensional case. For a three-dimension, all you have to do is add a third axis in the z direction, coming out of the page towards you. So, the same way as we have decomposed a vector in 2 or 3 or 4 or n other vectors, we can do the same thing with vector A, except this time we're going to pick those two vectors such that one of the two vectors is a line along the x direction and the other vector is a line along the y direction. Therefore, vector A can be decomposed as the sum of vector Ax, which is parallel to the x-axis, plus vector Ay, which is parallel to the y-axis, which means that vector Ax is perpendicular to the vector Ay. And therefore, we can write our vector A as Ax plus Ay. We can go one more step and consider a coordinate system which is orthonormal, which means that not only x and y are perpendicular to each other, but the unit length on each axis is going to be the same in the x and in the y direction. And I'm going to represent and use a new type of vector along the x direction, which I will call I, and along the y direction, which I will call j, whose magnitude is 1. So I will define what we call a unit vector, which is a particular vector whose length is 1. Therefore, the length of I is equal to the length of j, which is equal to 1. And I will use the convention that I is always going to be the one along the x direction, and j is going to be the one used in the y direction. Again, if you're doing three-dimensional, you can add another one, which we usually call k, which will be the unit vector along the z direction. So, what I can do now is, since vector I and vector Ax are parallel to each other, I can replace my vector Ax, which is a vector of length 1, 2, 3, 4, by 4 times the vector I. As if I take my unit vector I and I multiply it by 4, I will end up with the vector Ax. Therefore, I can write Ax as 4 times I. So the length of vector Ax is 4 times the length of 1. Similarly, in my picture, I can do the same thing with Ay, and I can replace this vector Ay by 4 times the vector j. And therefore the length of Ay is just, in this particular case, 4 times 1. So I can rewrite equation 1 using my unit vectors, and so vector A becomes 4i plus 4j, which can also be written in brackets. This is the component notation. Again, if you're doing 3D, you would just add a third vector k multiplied by a particular scalar alpha. Now, let's use this analogy to convert notation. Let's imagine that you're being given a vector b such that the magnitude of b is equal to 2 and its direction is 30 degrees. When nothing is specified, you can always assume that this angle is going to be measured from the positive x-axis going counterclockwise. In this particular case, the direction of my vector b has to be along this line, going towards the right and up. I also know that its length is 2, therefore I will use my unit length I j, and I will count it twice along my direction. This will give me my vector b. Now we need to be careful because the length of vector b is measured along the direction. Therefore, this particular length is not equal to 2, neither this one. It's the length of the vector which is equal to 2. Now, since we know that the angle between the x-axis and our vector b is theta, which is 30 degrees, we can use the Pythagorean theorem that allow us to find a relationship between the sides of this triangle. In this particular case, this is my vector bx, which is nothing else than the length times vector I, and this is my vector by, which again is by times j. So we would like to write b such as b can be expressed as bxi plus byj from this notation. How do we go from this notation to this notation? Obviously, all we have to do is figure out bx and by. But we recognize easily from this right triangle that we can use Pythagoras theorem and the relationship that goes with it, which means that the magnitude of b is going to be equal to bx squared plus by squared, and you take the square root. Similarly, bx is magnitude of b, which is the hypotenuse in this case, cosine 30, and by is b sine 30. And the last relationship is obtained by taking this equation and divided by this one, and we end up with tangent theta, or I'm sorry, is equal to by over bx, which we can use in order to find a relationship between theta, bx, and by. So the two relationships that we're going to use are those two, obviously. In order for us to get bx and by, all we have to do is take the length of our vector and multiply it by either the cosine or the sine. In our case, vector b will be 2 times cosine 30 in the I direction and 2 times sine 30 in the j direction. Now let's imagine that you were given a vector c defined as 2i minus j, and we would like to rewrite it such that we know its magnitude and its direction. So really we want to go the other way around now. All we have to do is use the two other relationship. This refers to Cx, so Cx is equal to 2, Cy in this case is equal to -1. Therefore, we know that C is related to Cx and Cy by this relation. Hence, we can figure out the length of the vector C by squaring each component and take it to the square root. In this case, square root of 5. Similarly, we can obtain the angle by taking the arctangent of the y component divided by the x component. In this case, -1/2. Now, there's always going to be a problem when you obtain and look for the angle. If Cx and Cy are both positive, you usually can trust the answer that your calculator is going to give you, which will be an angle measured from the positive x going counterclockwise. However, if your direction or your vector is either in the second quadrant, the third, or the fourth, you cannot trust the results of your calculator and you have to do one more manipulation. Let's figure out how to handle it. Let's imagine that your vector is in the second quadrant. Vector d will have a dx going towards the left and a dy going up. So if you express d in component notation, you know that dx is negative and dy is going to be a positive scalar. So when the calculator is giving you an angle, it's going to give you either this angle or this angle. Now, which one is it going to be? All you have to do is figure out and look up which component is the largest. For example, if, like in this case, dx is larger in magnitude than dy, and the calculator is giving you an angle which is less than 45 degrees, say 30 degrees, you know right away that 30 degrees must refer to this angle. Similarly, if dx is larger than dy and the calculator gives you an angle of 60 degrees, then you know that the 60 degree must be this one. So depending on which angle the calculator gives you, either you add 90 degrees if the calculator gives you 60, or you take 180 and you minus 30 degrees if the calculator gives you 30. So you have to be careful whenever you have a vector which is not in the first quadrant. Always check and figure out first in which quadrant the vector is, then which component is the largest, so you can figure out where the angle is measured from. Is it measured from the negative x going counterclockwise? Is it measured from the positive y going counterclockwise? For a particular vector in the third quadrant, you have to ask yourself, is this angle given by your calculator is measured from the negative y going clockwise, or is it the angle measured from the negative x going clockwise? So don't forget to make those two checks after you use this relationship.